This set of notes is about calculations of equilibrium constants and equilibrium concentrations. So up to this point, we know what equilibrium is. We know how to write equilibrium expressions, KEQ expressions. So what today is basically going to tell us is now if we're starting to be given some numerical concentrations or numerical pressures, how do we go about doing calculations related to those? So the first concentration that we have, or calculation that we have, is calculating K when all equilibrium concentrations are known. So this might be a problem like this. At equilibrium, the concentration of NO2 is 0.0172 m, and the concentration of N2O4 is 0.00141 molar. Okay, so there's our things. So the very first thing that we're going to do here is they've given us the equilibrium concentrations of everything. So we're going to go ahead and we're going to write the equilibrium expression. So Kc equals NO2 squared divided by N2O4. So there's our equilibrium expression. All right. Then all we have to do is plug and chug. So our expression, our equilibrium concentration for that goes in here. And our equilibrium concentration for that goes there. Go ahead and put those numbers in, do the plug and chug, and we should end up with a equilibrium constant of 0.211. Okay, so that was the easiest kind of calculation. So now, what happens if we want to calculate K, the equilibrium constant, when we don't know all the equilibrium concentrations? Well, in this case, we're going to use Rice tables, or otherwise sometimes called ICE tables. And this is just an acronym that stands for reaction, initial, change, equilibrium. All right, we would use it to solve a problem that sounds like this. A closed system initially containing 1 times 10 to the negative third molar H2 and 2 times 10 to the negative third molar I2 at 448 Celsius is allowed to reach equilibrium. Analysis of the equilibrium mixture shows that the concentration of HI is 1.87 times 10 to the negative third. Calculate Kc at 448 for the reaction taking place, which is, and then they give us the reaction. All right, so in this product, we're going to look and we'll see this is an initial concentration. This is an initial concentration. And that is an equilibrium concentration. Okay, so we've got concentrations for everything, but only one of them is an equilibrium concentration. So how do I go about figuring out what Kc is for this particular reaction? Now you'll notice these are listed as gases, so normally we would go Kp, but in this particular case, we've got 2 moles of gas beforehand and 2 moles of gas afterwards. So in this particular case, the number of moles is going to be the same on either side, so Kp equals Kc. They've also given us the concentration of these gases in molarity, so that would also tell us that we're going to figure out Kc here. So in order to solve this kind of problem, I've set up ICE tables, or Rice tables, to help us determine how many of the equilibrium values. Okay, so the very first thing that I do is I go ahead and I start with the reaction stoichiometry. So I put each of the species in along with their coefficients. So H2, I2, and then this is sort of our reactant product line, and then 2HI on that side. Okay, so the very first thing I'm going to do is set up a reaction line, put in the reaction stoichiometry so I can pay attention to that. So here's our problem again. Okay, and the next thing that we're going to do is we're going to fill in the knowns. So what do we know? Well, we know that H2 is 1.000 times 10 to the negative third molar initially. Okay, we know that I2 is 2.000 times 10 to the negative third molar initially. And we know that there's no HI because they didn't mention it in the initial system. Okay, then they also told us the equilibrium mixture has HI that is 1.87 times 10 to the negative third molar. Okay, so those are my knowns. So that's what I'm going to start with first. All right, next thing I'm going to do is I'm going to go ahead and I'm going to represent change using variables and numbers. So you'll notice that over here, we initially had none of this, and we went to an equilibrium concentration of 1.87 times 10 to the negative third. So what does that mean the change had to have been? Well, all of it, plus 1.87 times 10 to the negative third. All right. The next thing that we needed is we would know that the change here is minus some amount, and that there would be minus the same amount. How do I know that? Because we've got coefficients of 1. So however much of this gets used up, the same amount of that is going to get used up. Okay. We also will see here too that what does that mean that this is? Well, this means that this is positive 2x. All right, so then the next thing I'm going to do is go ahead and use stoichiometry to find the change variables. So we knew that this is 2x, which means that each of these have to be half of that on that side. So x and x have to be half of that, and there can be negatives. So if I half this, I get negative 9.35 times 10 to the negative fourth, negative 9.35 times 10 to the negative fourth, and 1.87 times 10 to the negative third. So that works out right there. Okay, then I've got a number here then and a number here, so I can go ahead and do subtraction. If this was what we initially had, and this is the change, so we're going to subtract 9.3 times 10 to the negative fourth, 9.3 times 10 to the negative fourth. That should give me my equilibrium concentration. It tells me what was used up. So into my handy-dandy calculator, those calculations go, and I get 6.5 times 10 to the negative fifth for the concentration of H2, 1.065 times 10 to the negative third for the concentration of I2, and then 2HI is what it is. Okay, so by doing that, we now have all of our equilibrium concentrations. And since we have all of our equilibrium concentrations, we can write our equilibrium expression from the balanced equation and then plug and chug. So first of all, write the equilibrium expression. So HI squared from the products over H2I2 from the reactants. Okay. And then we're just going to take those numbers, equilibrium numbers, out of the table on the previous page. And HI is 1.87 times 10 to the negative third. Okay. And then H2, 6.5 times 10 to the negative fifth. Concentration of I2, 1.065 times 10 to the negative third. Do the math, and I come up with a Kc of 51. Right, so those both were how do you calculate the equilibrium constant from concentrations. What happens if we have to go the opposite way? What happens if we have to calculate equilibrium concentrations from K? Well, the easiest version of this would be something that looks like this. At equilibrium at 773 K, Kp equals 1.45 times 10 to the negative fifth. If the partial pressure of H2 is 0.928 atmospheres and the partial pressure of N2 is 0.432 atmospheres, what is the partial pressure of NH3? Okay, so the first thing I'm going to do here is I'm going to go ahead and write my equilibrium expression. We've got everything in pressures here, so we're going to be writing Kp. Okay, and again, products, so the pressure of NH3 squared divided by reactants, pressure of N2 times the pressure of H2 cubed, okay? So rearranging this equation, because what we're trying to find is the partial pressure of NH3, so we want to find PNH3. And if I do that, so first thing I would do is multiply both sides by PN2 and PH2 cubed, right? And that gives me equals PNH3 squared, and then I would take the square root of that, and that gives me PNH3. Okay, so now what do we have? Well, we know the pressure of the nitrogen, 0.432. We know the pressure of the hydrogen, 0.928 cubed. And then we know the equilibrium constant, 1.45 times 10 to the negative fifth. And that then gives us our partial pressure of the ammonia, which is 2.24 times 10 to the negative third atmospheres. Okay, so once again, in this particular case, this is easy because they've given us K and they've given us the equilibrium concentrations for everything but the one we want to find. Okay, more complicated situation is calculating equilibrium concentrations when all we really know at equilibrium is the equilibrium constant. So it says a closed system initially containing 1.00 molar H2 and 2 molar I2 at 448 degrees Celsius is allowed to reach equilibrium. Kc is 50.5. Calculate the equilibrium concentrations of all three reaction species for the reaction taking place, which is those ones right there. Now you'll notice this is the exact same problem that we were solving earlier, except for this time they didn't give us the equilibrium concentration of this. They're saying, we're not going to tell you that. We're going to tell you what the equilibrium constant is. You got to figure out the concentrations, okay? So once again, we're going to go to Rice tables. So just like before, we're going to go ahead and step up our reaction initial change equilibrium. First thing I'm going to do is go ahead and put in my reaction stoichiometry, which is the same as it was before. H2, I2, 2HI, so I can figure that out. All right, so next, initial concentrations. So fill in our knowns. What do we know? We know that we've got 1.000 molar H2, 2.00 molar I2, no HI to start off with, okay? And we also know that our Kc is 50.5, but that's not going to play in here yet. Okay, so that's the first thing I do is fill in my knowns. Next thing I'm going to do is I'm going to use stoichiometry to insert variables for change. Okay, so again, HI is going to be increasing, so this is going to be plus 2x. These two are going to be decreasing, so minus x, minus x. Again, x, 2x come from the coefficients, 1, 1, and 2. Okay? Next thing we're going to do is we're going to use subtraction to fill out the equilibrium boxes. So we don't have numbers here to actually do the full subtraction, but we can say that this is 1.00 minus x, this is 2.000 minus x, and this is 2x. Okay? So the next thing we're going to do, now that we've got our table filled in, is we're going to write the equilibrium expression and substitute in for the equilibrium concentrations. So here's our equilibrium expression. Kc equals hi squared over h2 and I2. And then we're going to go ahead and we're just going to pull these in. So 2x squared, 1 times negative x, 2 times negative x. Okay? And that equals our equilibrium constant, 50.5. Okay, so I'm going to start solving this down, right? So solve for x using a calculator or rearrange to make it a quadratic equation. So if you know how to use your solver on your calculator, you can go ahead and just do that. But if you don't, we're going to rearrange it to make it a quadratic equation. So 4x squared, multiply both sides by this here, which is 50.5 times x squared minus 3x plus 2. So that's just this foiled down here, multiplied up on the other side. 45x squared minus 151.5x plus 101 equals 0. You'll notice that that then is a quadratic equation. And if it's a quadratic equation, we can solve it using the quadratic formula. So x equals negative b plus or minus square root b squared minus 4ac all over 2a. And if we do that, we get these two as solutions, 2.323 or 0.935 as solutions, okay? So if I then take that and I take x equals 2.32 and I put that into our equation, I end up with a negative concentration for H2, right? 1 minus 2.32 would give me a negative number, and we can't have negative concentrations. So the solution that we're looking for has got to be the 0.935. So then I simply take my 0.935, substitute that back into the equation line from the table. So x equals negative 9.35. So H2 would equal 1 minus 0.935. I2 would equal 2 minus 0.935. And HI would equal 2 times 0.935. And that gives me the equilibrium concentrations for all of my species. So those are the main kinds of problems you will solve using ICE tables. So again, always just, what are your initial conditions? What are they giving you? Fill that into the table. fill in the rest using either numbers or variables, and then go from there to make things happen and solve things out. So that's what you need to know about you making calculations using the equilibrium constant.